So let us start this session. Again, let me introduce myself. My name is Tanmay Sharma and I am a Prime Minister Research Fellow in the Mechanical Engineering Department of IIT Patna. And I am a teaching assistant of the NPTEL course on IC engines and gas turbines. And we are conducting this session so that we get you guys familiarized with the tutorials or what kind of problems that you will be facing in this course, and in order to help you go through the weekly assignments as well as your undergrads and also the postgrads subjects. So based on that, I have selected a few questions, and today in today's session we'll be solving dual cycle problems, and we'll be learning about the theory of carburetors, and try to at least solve one or two problems before ending this session. So let us first recall what are the air standard cycles that we have learned. So in my previous sessions and also through the NPTEL lectures, you must have read about the Otto cycles and the diesel cycle, which are very common. Like Otto cycle is the air standard cycle used for uh, determining the parameters of a spark ignition engine, and for a combustion ignition engine, the air standard cycle used is the diesel cycle, right? So the thing is that these two cycles are very different in respect to how the heat is added. So the heat addition process, okay, let us start that at one, it is the starting point, and after the suction process has occurred. But since it is a closed loop cycle, so there is no only the air flows throughout, and the air is not used for combustion. That is simply the heat is added to the air and it is not used for combustion. That is how air standard cycle works, and such kind of questions are also asked in the weekly assignments. So if you're asked that if the air is used for combustion, that is you should be knowing that only the heat is added through other medium, like in 2 to 3 here in the SI engine cycle, and in the diesel cycle 2 to 3 here. The heat is simply added to the air in order to increase the temperature and pressure, but the it is not used for combustion. So for the combustion, where the cycles wherein the combustion happens, it's totally different, and it does not entirely follows the Otto cycle or the diesel cycle. So after the suction you will be having, after the suction stroke you will be having at the conditions like in one, and from 1 to 2 there will be adiabatic this compression as the piston moves from the BDC to the top dead center, and the volume inside the cylinder, it becomes equal to the clearance volume that you can see out here. And 2 to 3, heat is added at constant volume in Otto cycle. 3 to 4 is adiabatic expansion, and 4 to 1 is again heat rejection at constant volume. Whereas in a diesel cycle, the heat addition is 2 to 3 at constant pressure instead of a constant volume process. And so we have derived in the previous sessions what is the this air standard efficiency of an Otto cycle, air standard efficiency of a diesel cycle. So air standard efficiency of an Otto cycle is basically dependent only and entirely upon the compression ratio. The compression ratio is the entire volume by the clearance volume, and that is the only governing principle upon which the Otto cycle air standard efficiency relies on. Whereas in diesel cycle you will have another factor, that is the this gamma and the rho. Rho is the cutoff ratio. So these factors are also affecting the efficiency in the diesel cycle. And if you are having the same compression ratio, so in that case, always the Otto cycle has the highest efficiency, whereas the diesel cycle has the lowest efficiency. We have seen that in our previous sessions. Then we have derived the work output out of these and the mean effective pressure. Similarly, for the diesel cycle, we have derived all these things. Now, we know that both of these Otto cycle and diesel cycle has their own advantages and disadvantages, but in order to give more time to the heat addition process, in order to see for an Otto cycle, the heat addition process is simply 2 to 3, and in diesel cycle it is 2 to 3, but What happens is, if the sufficient time is not given for the this fuel to burn, then there is incomplete combustion inside and there is a wastage of the fuel. In order to compensate for that, the dual cycle is made, wherein heat addition is both in constant volume process and constant pressure process. 2 to 3 is the constant volume heat addition and 3 to 4 is the constant pressure heat addition, similar to the diesel cycle. So accordingly, these have both the features of Otto cycle and diesel cycle. And in a previous session, we have derived what is the air standard efficiency of the dual cycle. We have derived the work output from a dual cycle and the mean effective pressure. So by mean effective pressure, as I have already explained in the previous sessions, so what we mean is that if we this is the pressure and the uh, volume, pressure against the volume is fluctuating and throughout the entire cycle. So the pressure is not same, but if we want to simply find what is the pressure, if we simply multiply that pressure with the net volume displacement, we should get the entire work. So if we find that particular pressure, that pressure is called as the mean effective pressure. So that is a constant pressure. So you can have, instead of a complicated graph like this, you will simply have a cube or a square or a rectangle. Sorry. So yeah, so that square, you will have a constant pressure out here, and the volume in which the constant pressure applies. If we multiply the volume, that volume, with the constant pressure, you will get the net work done out as here. So that pressure, constant pressure, is called as the mean effective pressure, and this mean effective pressure is has the expression like this. So it depends upon the gamma, that is what type of gas it is, that is simply the ratio of the specific heats. Then beta, beta is simply the ratio between the 5 and the this V4, and then rho, that is the cutoff ratio. Then again, compression ratio 1 and 2, between the volumes 1 and 2, that we have, and accordingly this expression we have right now. So I think there should not be any problem till now, because we have discussed in the previous session. Anyways, I will just have a look if there is any doubts. Okay, so there is no doubts. Okay, then I will continue. So what I plan to do is that we haven't discussed in detail about the problems related to the dual cycle in the previous sessions. So here I have taken a few problems from the book R.K. Rajput, and let us see how to go through these problems. Like this, for instance, this is the first problem that I have taken, which is a little bit complicated than the previous problems which we have discussed in the previous sessions. So let us have a look at this, how to solve this, and you will get an idea how to solve problems related to the dual cycle. So let us read this question and take some time to absorb this. So the compression ratio for a single cylinder engine operating on a dual cycle is 9. So we have the compression ratio as 9 R. The maximum pressure in the cylinder is limited to 60 bar. So okay, the maximum pressure is given. The pressure and temperature of the air at the beginning of the cycle is 1 bar and 30 degrees Celsius. Okay, the inlet conditions are given. The heat is added during constant pressure process up to 4% of the stroke. Okay, at the constant pressure process up to 4% of the stroke. So the if we draw the diagram, we know that this is constant pressure heat addition process, and here at 4% of the stroke, the heat is being added at constant pressure. So then we have to assume that the cylinder diameter and the stroke length are 250 millimeter and 300 millimeter respectively, and we need to determine the air standard efficiency of the cycle and the power developed if the number of working cycles are 3 per second. So the air standard efficiency of the cycle, if we know the formula, then we can simply put in the values. First we'll find the values of the R, beta, gamma and everything, and after that we will simply plug in the values into the formula, and we will get the air standard efficiency. That is quite easy, but knowing the formula is a little bit difficult, right? So instead, if you are very familiar with the graph and you are very familiar with the thermodynamic relations, you are very confident that you can find the relations very quickly, then you can quickly find what is the net work output and what is the this what is the total heat input. So based on that, you can directly find the air standard efficiency of the cycle. Either ways, it is for. And the power developed if the working cycles are 3 per second. So that we will see how we will solve that. So I will give you like 1 to 2 minutes to think on this, and after that I will try to solve this problem. So if there are any doubts afterwards, I will try to clear them. Okay, then you guys can think on this problem, how to do that. Okay, guys, I think you guys are trying out in your end. So let me go through how the solution looks like here. So for air standard efficiency, first we find out the swept volume. So what is the swept volume? So this is the part in which the piston has traversed from the bottom dead center out here to the top dead center out here. So this part, the piston has swept, right? So that is the swept volume, Vs, and that we are already given the cylinder diameter and the stroke length. Accordingly, we can find the swept volume. Then the swept volume evaluates to be this, and after that we find the compression ratio. If we know the swept volume, we know the clearance volume. So if the clearance volume is given or not. um so let us see. So we do not know the clearance volume, but we know the compression ratio. So we can find the clearance volume out here by Vc, and accordingly we will get Vc equals to 0.0018 meter cube. So we found a Vc, and that will be needed because the Vc is equal to V2 as well as V3. And from if we know V3, we can directly get V4 because that is related to Vs, which we know now. And V1 also we can get by total the sum of these two volumes. And next, I think you have got this. So the V1 is 0.0165 meter cube. So V1 we know, P1 inlet condition we know as 1 bar 30 degrees Celsius. V2 we know, so we can simply start from this point and go through all the thermodynamic relations and evaluate the points at 2, 3, 4, and again 5. So let us see how we can do that. So for the 1-2 process, that is adiabatic expansion or isentropic process. So sorry, adiabatic compression, not expansion. The expansion is this process. This is adiabatic compression or isentropic compression. So in that we know the isentropic thermodynamic relationship as this P1 V1 gamma equals to P2 V2 gamma. And we know now what is P1, what is V1, what is V2, but we do not know what is P2, right? So from here we will evaluate this as this V1 by V2. So V1 by V2, which is nothing but the compression ratio, right? So simply compression ratio to the power gamma 9 to the power 1.4 is 21.67 bar. So sometimes what happens is that air or the fluid that is passing through is not given, rather the specific heats are given. Then to find the gamma, you will simply have to take the ratio of both. So here, um, since air is already mentioned, you can directly go for 1.4, but again, the Cp and Cv are given. So Cp by Cv is gamma. You can see how this 1.4, if it is justified or not. Simply take the ratio of Cp by Cv and you will get the value of gamma. Then also temperature and the volumes are also related by this in the isentropic process, and we can find the temperature in T2 if we know the temperature at T1, and that is how we will get. So T2 is T1 into this compression ratio to the power gamma minus 1, and accordingly we will find the value of T2. So we have found all the things for T2, sorry, point 2, and now we'll find the values of point 3 out here. So this is uh, here what happens is that we will take the Q of what is the heat added during this process, or the type of process that we are following. So this is a isochoric process. The volume is constant, right? So accordingly we will have constant pressure. Okay, so first we will see for constant pressure process, that's also okay, because point 3 and 4, 3 and 2 is known. Accordingly, V4 by V3, this is the cutoff ratio, we will calculate as 1.32. How can we calculate that? So simply V4 is 0.4 times of Vs, and V3 we know now as Vc. So simply if we can calculate that, because we know Vs, so we can calculate that the value of rho, and we will get the value of T4, or the temperature at 4, which is the highest temperature in the entire cycle, that is 2666 Kelvin. Then the expansion ratio, or 4 to 5, see, so V5 by V4, so V5 by V4, that is the expansion ratio. So that can be calculated in terms of the cutoff ratio as well as the uh, compression ratio. How? So you will have to just manipulate a little bit. So we have introduced the term V2 in here. So V5 by V2, so V2 by V4. So this actually get cancelled. So we have simply introduced out here. It does not affect the ratio. And then V5 by V2, V5 by V2, that can also be written as V1 by V2, because V5 equals to V1. So instead V5 we have replaced by V1. V1 by V2 we know as the compression ratio. Then V3 by V4. So V2, here V2 we have replaced by V3. So V2 is replaced by V3 because these are same. And we know that V4 by V3 is the cutoff ratio. So accordingly, the expansion ratio V5 by V4 can be found out in terms of the compression ratio and the cutoff ratio. Then V5 equals to V, so that is the explanation out here. And for the adiabatic process 4 to 5, we need to find the temperature um, as T5, as because we know the temperature of T4, so T5 we will find out as, in this process, 1237 Kelvin. So now what we know is that we know the temperature of 4, we know the temperature of 5, 1, 2, everything we know till now. So it will be helpful for us to find the air standard efficiency of the cycle. So for the we should know the values of the P4 as well as P5. So for that we will calculate based on P5 equals to P4 and V4 by V5, and the maximum pressure. So that part is very important. So the maximum pressure was already given in the problem, that is 60 bar. So this bar is 60 bar. So P4 and P3 we know. We do not know the P5. So from here we will get the P5 value as V4 by V5. Again, V4 by V5 we have just calculated it as rho by R. So that, oh, okay, sorry, R by rho. And we can calculate what is P5. It so is happening 4.08 bar. And now we will calculate the total heat supplied. So total heat supplied is the heat is added at constant volume at here and constant pressure at here. So we will use this formula. So CV into delta T and CP into delta T. So why CV? Because specific heat at constant volume will be applied for this heat addition process 2 to 3. So simply T3 minus T2. And this process here we will have to use the specific heat at constant pressure CP, and the delta T is T4 minus T3 out here. And accordingly we will have, just plug in the values. We have just calculated T3, then T2, T4 also we know, then T3 also we know. Then it will come as total heat supplied as 15,062 kilojoule per kg of air. We know the heat supplied. If we know the work output, then we can directly get the air standard efficiency of the cycle. So next, to get the work output, if we know the heat rejected, we can directly find the work output by simply subtracting the both heat supplied minus heat rejected. So that way we should find the heat rejected, and we know the heat is only rejected at this particular part, 5 to 1. So that is a constant volume process, 5 to 1. So for that we have used the specific heat at constant volume CV and T5 minus T1. We have calculated the values of T5. We are known in the problem the value of T1. Eventually we will put all the values and we will get the QR to be 663.14. Now the air standard efficiency can be directly given as work done by heat supplied, and the work done is the so that what happens in an engine is that from the source heat is supplied, and the heat, some amount of heat is rejected to the sink, whereas other part of the heat is utilized in driving output work. So that part is the subtraction. So QS minus QR is the amount of work that is driven by the engine, and divided by QS, which is the heat supplied. Accordingly, we will get the air standard efficiency as this. So even though we have solved the or derived the air standard efficiency in terms of other these numbers, and we find that sometimes remembering the whole expression is quite tough. If we follow this strategy, we will find the salient points at all the salient properties at all the points, like 1, 2, 3, 4, and 5. Eventually we will calculate what is the heat supplied by the constant volume heat addition, constant pressure heat addition, and we will find what is the heat rejected at constant volume. And after that we can directly find the air standard efficiency with this particular formula. You can go in this way also, like what is the work done, and what is the work done is basically you will find this is 1 to 2. Here the work is being done. So here the work is done on the system, the expansion system. So 1 to 2 is the work being done on the system. Get the the network, but that is a little bit complicated. Instead you should follow the heat components. If you find the heat components, you will simply get the air standard efficiency very quickly. So we are done with the first part, air standard efficiency of the cycle. Then the next part is the power developed if the number of working cycles are 3 per second. Okay, so cycles per second. So that is the RPM by which we can calculate the RPM out here. So let us see how to calculate this. First, we will have to calculate the mass flow rate of air. So mass flow rate if is generally calculated based on the point 1, but anyways you can calculate on other points as well. You will get the same value because mass is conserved within the system. This is a closed loop system, and you will find that the air is not added as well as the air is not lost, as it is not seen in the practical system, where in the from the inlet manifold the air comes inside, and from the exit manifold it is escaped in each cycles, right? But here this is a closed cycle, and here you will find the mass is conserved. So at any point, if you just calculate based on this ideal gas law, then you will find the value of mass flow rate of air. So for the point 1, we calculate from point 1, the P1 V1 by RT1, we will find the mass of air in the cycle is 0.189 kg. But that is, we are not, we need to find out the power, which is a rate of work done. So if rate is given, then we will have to see what is the mass flow rate, not the entire mass which is present. So accordingly, we'll have to find the mass flow rate, which we will do later. So simply we will use this particular information in the question. So the work done per cycle is given as m qs minus qr. So qs minus qr is the heat supplied minus heat rejected, that is the work done in the cycle. So m into work done, and accordingly we have the kilojoule, but that we do not need, we need kilojoule per second or kilowatts. So power developed is the work done per cycle into number of cycles per second. So in one cycle, we know how much work done is there. What is the number of cycles per second? If we simply multiply it, we will get what is the power developed, and that is 51 kilowatts. So it is very important to understand what is power and what is work. So work, the power is the rate of doing work. At what time you will be completing that amount of, you will be transferring that amount of energy. That is the power, right? So both things are different, and you need to stay focused on what the question asks. So by this we have completed the first question of our session, and we will quickly move on to the next question. But before that, let me see. Admitted. Right. I think now it's admitted. Okay. I will continue with my next question. Okay, then let us go on to the next question. So in this session, we will have three questions of dual cycle, which is an air standard cycle. And for the people who have joined just now, so actually I was uh, uh, giving some problems which I have taken from the book Internal Combustion Engines by R.K. Rajput, and we will see how to solve these problems, which will really help you in solving the questions in your undergrad courses as well as in the postgrad courses or in other competitive exams. So that's why I have put up these questions, and if there are any doubts, you can just put your mic on, and you can ask, or you can just comment there. I will see time to time. So the next question is, in an engine working on a dual cycle, the temperature and pressure at the beginning of the cycle is 90 degrees Celsius and 1 bar aspect. So at the inlet point 1, we are given the uh, conditions of the temperature and pressure. Then the compression ratio is given as 9. So we know the compression, that is very good information. The maximum pressure is limited to 68 bar. Okay. And the total heat supplied per kg is 1750 kilojoule. So that is kilojoule per kg. And we need to find the pressure and temperatures all cell in points, A standard efficiency, mean effective pressure. So we have already calculated the pressure and temperature, how means the procedure how to calculate the pressure and temperature at all points. But for the newcomers to this session, this would be a little bit beneficial. I will again repeat this. So this is the diagram that we have, which is very similar to the previous diagram as well. But the question is a little bit different. We are given the temperature and pressure at the beginning of the cycle. So this is the beginning of the cycle 1, and here we know the pressure and temperature, and so we are also given that the compression ratio is 9. So V1 by V2 is given as 9. That is good. Then the maximum pressure limit is 68 bar. So 3, 4, at these points the pressure is 68 bar. and the total heat supplied per kg is 1750 kilojoule. So that is 1750 kilojoule per kg, and the heat added in the dual cycle is at constant volume 2 to 3 and constant pressure 3 to 4 process. These are the processes where the heat is added, and the net heat added is total is 1750 kilojoule. Then the heat is rejected by 5 to 1, and that we will have to see later when we need to find the air standard efficiency. So let us think how to solve this problem. We know all the thermodynamic relationships. From that, we will have to calculate the pressure and temperature, all salient points. So I will again give like 1 minute to think about this problem, and then I will solve this problem. The people who have joined this meeting a little late, they can now take the cue from this problem and then solve the next. And the other people, they know now the procedure. They can directly start solving these problems. Anyways, so let me show you how this problem can be solved. So first, let us find the pressure and temperature at all the salient points. So at 1, we already know the pressure and temperature. 3 and 4, we know the pressures. At 2, we know the volume, but not pressure. At 5, we know the volume. Do we know the volume? No, at 2, we do not know the volume, but we know the compression ratio. So from that, we will get the volume out here. Now, let us see. So this is the 1 to 2 is the adiabatic or the isentropic process, isentropic compression, and we have the thermodynamic relation as is here. Then from here we can directly find P2. So P1 we know, V1 by V2 is given as the compression ratio is given as the 9, and we will directly plug in the value 9, and gamma, since this is an air standard cycle, so per kg of air, and for air we should always memorize this value. The gamma value is 1.4, which is the ratio of the specific heat of constant pressure divided by specific heat of constant volume. So accordingly we will plug in the values. So r to the power gamma, so 21.67 bar. So P2 we got, that is the first part. Then T2 we can again calculate from this expression, which is again related to the compression ratio. So you can see here, and eventually you will get the temperature as T1 into 2.408, which will be given as 874.1 Kelvin. So here we know the pressure and the temperature now, right? I'm sure you must have done by the same way. Then we already given the pressures at 3 and 4, that is 68 bar, and we now know the temperature and the pressure at part 2. So this is the constant volume process, so you must be knowing what I'm thinking. So we just use the process law, and by that we will get the values at point 3. So simple constant volume process 2 to 3. So P2 by T2 is equal to P3 by T3. We know P2 and we know T2 now. We are given the value of P3. So we can simply find the value of P3 as this, T2 into P3 by P2, and it will get, you will get the value as 2742.9 Kelvin. That is quite high value, but not the highest. The highest value is at 4. So next we will see the heat added at constant volume, that is Cv T3 minus T2. Now we are know what is T3 and what is T2, right? So we can use the this expression. And why we use Cv? Because this is a constant volume process. So we'll have to use the value specific heat at constant volume, not specific heat at constant pressure. and accordingly we will get the value if we plug in the values as heat added at constant volume is 1326 kilojoule per kg. So this part is 1326 kilojoule per kg, and we know what is the total heat added, that is 2 3 plus 3 to 4, right? That is 1750 kilojoule per kg of air. So now we'll simply have to find what is the heat at constant pressure out here. Simply total heat divided, minus the heat added at constant volume. Plug in the values, you will get only 423 kilojoule per kg is being added out in this constant pressure process. Okay, then we know what is the expression of heat added at constant pressure process. That is simply we'll have to use the specific heat at constant pressure into the delta T will be T4 minus T3. So T4 minus T3 because of 423.2, and eventually you will get the value of T4, that is what we are missing, and you will get the value of T4 as 3166 Kelvin. So T4 is the highest temperature, and this is at 3166 Kelvin, and you are limited by the pressure 68 uh, bar. And why we limit the pressure at 68 bar? Because in this there is a in these questions you will find that the maximum pressure is given already. So that is a design parameter of these questions. So because the this 68 bar or the maximum pressure is basically designed as per the breaking limit of the material that is used to manufacture the whole cylinder. And if you exceed that breaking limit, that will permanently damage that cylinder, and it will have leaks, and it can cause explosion. And that's why, to minimize that, we are given through a factor of safety what is the maximum pressure at which we should design the whole engine. So that is 68 bar, and accordingly the highest temperature you will reach is 31 Kelvin. Next, we know the constant pressure process 3 to 4, and so V4 by V3, that is the cutoff ratio. So that is equal to T4 by T3. We now know T4, we already knew T3. Simply the cutoff ratio would be 1.15, and for this adiabatic expansion process 4 to 5, we will have to find what is the ratio of V5 by V4. So that is the expansion ratio, and the expansion ratio, as I have already explained in the previous problem, so we will manipulate the ratio a little bit. So we introduce V2 in both. So now V5 can be replaced by V1 because this is the same volume. So V5 is replaced by V1. Then V2 here, V2 out here can be replaced by V3. So V2 out here is replaced by V3. And now we know what are these ratios. V1 by V2, that is simply the compression ratio, R, and V4 by V3, that is 1 by V4 by V3 out here, V3 by V4. So that is the cutoff ratio out here. So V4 by V3. So that is cutoff ratio. Accordingly, we will find the expansion ratio is related to the compression ratio and the cutoff ratio as like this. Then now once we know what is the ratio, expansion ratio, we can simply plug in the uh, this thermodynamic relation for the isentropic expansion process out here 4 to 5, and by that P5 we will get as 68 into rho by r to the power gamma, and accordingly we will get 1.15 divided by 9 to the power 1.4, and it will be 3.81 bar. So by that we get P5, and I think we have got all the pressure and did we get the temperature? I think we did not get the temperature. We know the volume though. So next we have to calculate the temperature. So that T5, we know the T4. I simply plug in the values to in this thermodynamic relationship, and you will get T5 equals to T4 into 0.439, that is 1389 Kelvin, 1390 Kelvin. So by that we get what are the pressure and temperatures at all salient points out here. Then If we know all the pressure and temperatures, can we find the air standard efficiency? But the easy method, right? So we can simply use the easy method rather than just following the derived expression of air standard efficiency. Although if we can plug in there, you will get the direct value of air standard efficiency, but that is quite mm, hard, because it is very hard to remember those formula. So QR, heat rejected during constant volume process 5 to 1, QR is this part, is CV into T5 minus T1, right? Constant volume, so use CV, that is a specific heat at constant volume, and the delta T is T5 minus T1. Accordingly, you will have heat rejected value as 729 kilojoule per kg. Total heat supplied is, we know, 1750 kilojoule per kg. So we can directly calculate the air standard efficiency as work done by heat supplied. That is QS minus QR by QS, which is equal to 58.34%. So this way we can calculate the air standard efficiency. There is an alternative method. You can direct plug in the values of this compression ratio, then the cutoff ratio, expansion ratio, and the gamma value. Everything if you put, you will also get the value, but that is quite hard. If you quickly find all the salient points of the pressure and temperatures, if you have the habit, then you can just plug in this particular expressions and you can find the air standard efficiency. Next, the mean effective pressure. So again, if we know the work done, then simply divided by the stroke volume, we will get the mean effective pressure. We need not memorize the formula for that. All right. So we know the work done, that is heat supplied minus heat rejected. By that also we can do, or from here also we can simply work out, like this P3 into V4 minus V3. So P3, V4 minus V3, there is a constant pressure heat addition. So in this process, the volume is changing. So again, if for a closed loop system, okay, that is very important. For a closed loop system, this is a work done. So because that is P del V work is being done. If it was open loop system, then it would have been VdP, and for VdP the dP or the delta P is 0 because the pressure is not changing. For that the open loop work done is 0, but now this is a closed loop system, so for that a work is being done at this because the piston is moving, it is displacing, and accordingly the work is being done. So that is P3 into V4 minus V3 here. Then again P4 V4 P5 V5. So you see here this is the expansion process, and here during the expansion of the gas, the force is being exerted on the piston, and it is moving the piston downwards from the top dead center to the bottom dead center. Accordingly, the revolution of the shaft is happening, so the work is being done, work is being driven out from the engine. We are getting a work output from that, so that is positive. So P4 V4 minus P5 V5 divided by gamma minus 1, that is adiabatic work done, right? And where we are consuming the work, so that is the expansion process, where the piston from the bottom dead center, it moves to the top dead center, it compresses the gas, and we have to do work against compressing the gas, right? That is P2 V2 minus P1 V1 divided by gamma minus 1. So that is the negative part, that is work done on the system, and this is work done by the system. And we divide the entire work done divided by the stroke volume, and by that we can simply plug in the values. So we will have to do a little bit manipulation of what are the volumes out here. So you must be now familiar right now with this. So if we smartly plug in the values, everything, and all the values that we have found out here, we will get the value as mean effective pressure as 11.04 bar. But other way around, if we simply use heat supplies minus heat rejected, that is kilojoule per kg, divided by stroke volume, you will get the same answer. You need not do it this way, but in order to show you that it can be done on the other way around also, that's why I have selected this problem, and now you know. So the mean effective pressure is 11.04 bar, and that is the answer. So by this, we have completed the second problem of this session. Is there any question? Let me just see. Okay, no question. I can move on further, but please feel free to ask any questions because it is expected to be a interactive session rather not a simple lecture delivering session. So I hope that I am showing you some problems which are a little bit conceptually hard so that you can find some questions and you can clear it out right now. So let us move on to the next problem of this session, that is an IC engine operating on dual load, the limiter pressure cycle. The temperature of the working fluid air at the beginning of the compression is given 27 degrees Celsius. Okay. Then the ratio of the maximum and the minimum pressures of the cycle is 70 and the compression ratio is 15. Okay, that's interesting. What ratio of the maximum and minimum pressures of the cycle? So if you know the cycle very well, then you can directly get to know what is this ratio. And the compression ratio is 15. Okay. The amounts of heat added at the constant volume and at constant pressure are equal. Okay, that is a good thing. So compute the air standard thermal efficiency of the cycle and state three main reasons why the actual thermal efficiency is different from the theoretical value. That is also quite interesting. So this question came in UPSC 1997, and based on, so this is what a dual cycle looks like. You, so now, as per the question, it is given that the beginning of the compression, the temperature is given at T1 is given, then the ratio of the maximum pressures and the minimum pressures. So by now you know that maximum pressure is this, since this is the P in the y-axis, V in the x-axis. So maximum pressure is 3 and 4 out here. So P3 and P4, that is equal and it's the maximum. And the minimum pressure is out at 1, so P1. So basically P3 by P1 or P4 by P1 is given as 70. And the compression ratio is given as 15. So V1 by V2 is given as 15. Amounts of heat added at constant volume and at constant pressure are equal. So heat added at constant volume is 2 to 3. Heat added at constant pressure is 3 to 4. And these two entities are equal. That is good. So by that we can equal and we can find the temperatures. So that is how we should be thinking. So again, let me give you guys some time to think on this problem, and then I will show you how to solve this problem. Okay, then let me show you how the problem is being done. I am sure you must have already got the gist of how to do this or solve this problem. So first, we will always consider 1 kg of air when there's no mass related questions in the question. So first we will be solving for the air standard efficiency. So now the in order to solve that, we will have to get through all the points in the whole cycle. So in order to find all the points, this is the first, we will follow the process 1 to 2, which is the isentropic compression process. and then V1 by V2 we know the compression ratio. So this is the expression, and V1 by V2 we are known value is 15. Then we will simply get the value of T2 as 826.2 Kelvin. Okay, again we will find the value of pressure. So simply plug in the values in this equation. You will get P2 equals to 44.3 P1. So P1 we do not know for now. So only the T1 or the 27 degrees Celsius at the beginning of the compression is given, but the pressure it is not given. Okay, we do not need that, right? We only are concerned with the maximum pressures, and we will get to that. So for the constant pressure process 2 to 3, we know P2 by T2 equals to P3 by T3. Then T3 equals to P2 into P3 by P2. Now we will substitute the value of P2, which is P1. So by this, we will now get the exact ratio, because we are given P3 by P1 is 70, right? So simply we will plug in the values and we will get T3 to be 1400 Kelvin. T3 is 1400 Kelvin. T2 we know. Then the amounts of heat added are equal. So if we simply equate this, I think we will get the value of T4. So let us see. The heat added at constant volume equals the heat added at constant pressure that is given. So simply we will equate this Cv T3 minus T2, so that is the constant volume, Cp T4 minus T3, that is constant pressure, and then simply we do not know the value of only T4 and rest we all know. Then we will get the value of T4 as through these equations to be 1767 Kelvin. So now we know the value of T4, that is this, the highest temperature. Then what we need to compute the air standard thermal efficiency of the cycle. So for that we need to know the heat rejected, so we need to know the T5 as well. So for that we will consider this process T4 4 to 5, which is the isentropic isentropic expansion. Also first let us consider the constant volume process 3 to 4. So T3 equals to V4 by T4. Accordingly, we will get what is the ratio of V4 by T3 or T4 by T3. That is simply 1.26, and V4 by V3. So V4 by V3 here, what is V3? V3 is simply we can relate to the compression ratio 15. So V1 by V2 or V1 by V3 is 15. From that we will get this particular relation, and if we put this relation, and which is equal to 1.26 that we have just now solved, then we will get V4 and V5, V1 with a relation among them. So V4 is this, V1 is this, again V1 is again V5, right? So among V4 and V5 we got the ratio of 0.084. So that is quite comforting, because now we know what is V5 by V4 or V4 by V5, and then we can now solve for the temperature by using this relation. T4 by T5 equals to V5 by V4. Now if we solve it, we will get the value of T5, because T4 we know as 656.9 Kelvin. Then if we know the values of all the temperatures, we can now calculate what is the heat added and heat rejected, and what is the net work done. So net heat supplied minus heat rejected divided by heat supplied. So we can find these relations based on the temperature values out here, and this is the air standard efficiency. So 1 minus heat rejected by heat supplied, that is this particular formula we will get. We will just have to plug in the values, and we will get the value of air standard efficiency to be 65.3%. So that is how the problem is done, and I will take up any questions if you have any questions still here. And next we will move on to the carburetor section. So till now we have solved what is the some complicated problems of dual cycle, And you can follow the book Internal Combustion Engines by Rajput. You can follow, you can solve more problems out there. You can get more familiarized with this, and even though you are knowing how to solve these problems, I think you will be able to solve any problem related to dual cycle. And in my previous sessions, if you follow the questions solved for auto cycle and diesel cycle, you will be familiarized with how the problems are coming, and eventually you will get to solve, you will be able to solve all the problems of that domain. So let me first check if there are any questions, then I will move on to the next topic. Hmm. Okay, is there any question? Mohit, you have told yes. If no, then I can go ahead with it. No issues. Okay, then I'm assuming there's no question. So let me go ahead. So next part is actually so okay, we were left by one question, one slide question, which is a conceptual question. State three main reasons why the actual thermal efficiency is different from the theoretical value. So the actual thermal efficiency being different from the theoretical value is there are two significant points. So in the first is the in theoretical cycle, working substance is taken as air, whereas actual cycle, air and fuel acts as working substance. That is the case because if the substance is different, the thermal efficiency will be different because the value of the gamma will be different, value of the Cp and the Cv values will be different. So everything will be different, and accordingly the thermal efficiency will be different. Again, the fuel combustion phenomena and associated problems like dissociation of gas, dilution of charge during suction stroke, etc., have not been taken into account. So this is a very good problem. Means uh, actually a very uh, we do not have any control about the dilution of charge and everything, and this needs to be discussed, and I will discuss it when we are talking about the carburetors. So what happens is that when the engine in the exhaust stroke, all the gases from the engine cylinder are not removed during the exhaust stroke, and there is some amount of burnt charge which is exhausted that remains, and it gets added up with a new fresh charge. So the amount which it can accommodate inside the cylinder, that is the same, but in the same volume some amount of unburned mixture is present, and the amount of some amount of burnt mixture is present, and the fresh charge, it is a little bit less. Accordingly the efficiency will decrease because the unburnt has no contribution, rather it only occupies some space in the combustion process. So in that way, the efficiency will decrease, the actual thermal efficiency will be different from the theoretical value. And we'll talk a little bit more elaborately in the next carburetor section. So let us move on to the carburetor section out here. So before moving to carburetor section, let us know how an induction system, what is an induction system, and how the fresh charge is inducted into the cylinder. So basically, during the motion stroke or the suction stroke out here, so this is basically the schematic of a very simple schematic of induction uh, manifold. So this is an induction intake manifold or induction manifold out here. This is the intake valve, and at the upstream of it, so there is a carburetor, and the air passes into the carburetor, the fuel also passes, and the carburetor is responsible for making the mixture of air and fuel in SI systems, in petrol engines, and the air fuel mixture is then passed on to the cylinder, wherein through the intake valve. So here there would be a spark plug which will ignite the air fuel mixture, and eventually the whole process will take place. So this is an induction system, and what happens is that during motion stroke or the intake stroke, as the piston moves downward, so the piston moves from top dead center to the bottom dead center, then a empty space is created out here, and that is nothing but the vacuum. And when a vacuum is created, it actually drives the air and the fuel from here into the cylinder. So that is, the vacuum is created in the cylinder, which causes the air flow through the carburetor and the fuel to be sprayed from the fuel jets. Now what happens is, the fuel in the carburetor, it is actually sprayed upon the air. So why spraying? So what happens is that if you are spraying the fuel, so that is, spraying means a very tiny mist of the oil particles. Now very tiny mist or the drop. So in very cold seasons, you must have felt that there is too much fog, and when you pass through the fog, these are nothing but the very small droplets of mist, and you will find your face is getting moist. So that is mist. It is very small droplets of water, but here we are talking about droplets of fuel. If you have very small droplets of fuel, which is a very small volume, then the surface area is quite high, and it can easily get the fuel droplets can easily get vaporized and get mixed with the air. So eventually we need a vaporized mixture of fuel and air, not fuel in liquid phase. Only then that can be easily ignited inside the cylinder. So that's why the fuel is spread in terms of fuel jets. Then again, this I have explained. So the fuel, generally the volatility of the fuel is commented upon by the number octane number you must be hearing, and we will discuss that in the subsequent sections. So the if the fuel is volatile, and if you are reducing this volume and increasing the surface area, there is higher tendency to vaporize. So the fuel will vaporize and form combustible fuel air mixture out here. Next, so although we are taking care that it vaporize, but somehow the larger drops may reach the cylinder in the liquid form, and it must be vaporized and mixed with the air during the compression stroke before electric spark ignites the mixture. So that part, some amount of liquid fuel also goes. So here in the weekly assignments, you must be asked one question, that what is the state of the air fuel mixture which is entering uh, from the carburetor into the cylinder. So at the outlet of the carburetor, the state of the air fuel mixture is that it is partially vaporized, not completely vaporized fuel. So for a partially vaporized fuel, there will be some amount of fuel in the liquid form, and that the liquid form, if we try to ignite the liquid form, it will take higher time. It will actually not ignite, and then we need to actually vaporize the liquid fuel into vapor form, homogeneously mix it with the air. Only then we can ignite the fuel air mixture. So in order to do that, what happens is that the cylinder is itself very, the temperature and the pressure condition inside is very high, right? It is high temperature, high pressure. In that condition, what happens is, this larger drops, although it is liquid, it automatically vaporizes because of the high volatility of the fluid. And that is, the high volatility is actually needed in this kind of engines. And that's how, so when an electric spark is created, there will be homogeneous burning of the fuel, and the flame which will be created will be having a very uniform flame front, and we will discuss about this in the subsequent sections. Then the next part is that there is a limited range of the air fuel ratio in a homogeneous mixture within which the combustion in the SI engines are sustainable. That is good. So air fuel ratio, what do we mean? So some amount of in a charge per means per second, how much air is being injected and how much fuel is being injected after homogeneously mixing. So that is the air fuel ratio. Okay, and there's a range at which the engines operate this air fuel ratio. So for example, the outside this range, the ratio is too rich or too lean to sustain a flame propagation. And what do you mean by lean? So like 20 is to 1. So 20 parts of the mixture is air. Only one part of the mixture is fuel. That is, air is too much in excess. That is quite lean, right? That is very lean. So in that case, the fuel actually it will not ignite properly. Means even it ignites, there is not too much heat is added into the process. That may happen. And 8 is to 1 is rich. Why? Only 8 parts of air is present, whereas one part of fuel is present in this mixture. And in order to completely burn this fuel, we do not need 8. We need actually a little bit more in order to completely burn. So some part of the fuel will be left unburned, and which is also a wastage of fuel, and it will lead to other complexities. So we need to design such a device which only supplies the best possible mixture in order to have a very good combustion inside the cylinder, and that device is the carburetor out here. And we need to very properly design this carburetor in order to uh, satisfy the range of the air fuel ratio, and we will talk about this in the next slides, the what is the useful air fuel ratio and different conditions. So that was the a slight introduction of the induction system. And we have a question from the weekly assignments. So the function of the induction system of a spark ignition engine is to supply dash to various cylinders of the engine. So here, now, as I have already explained, the function of the induction system is to supply partly vaporized mixture of the fuel and air, not fully vaporized mixture, partly vaporized mixture. Okay, and so this is the answer. And why partly? Because it is not able to completely vaporize the entire thing, and the rest part which is left unvaporized, that is being taken care of by the high temperature and the pressure inside the cylinder. That is automatically contributing to the vaporization of the fuel, which is left unvaporized at the outlet of the carburetor. So that is the question, and this is the answer. Next, let us move to a carburetor. So here I am showing a very simple sketch of a carburetor arrangement, which is present in the SI engines, spark ignition engines. So carburetor is only present in the spark ignition engines, where air fuel mixture is supplied inside the cylinder, but in the compression ignition engines, only air is supplied into the cylinder, whereas the fuel is injected inside the cylinder at very high pressure and temperature conditions, and through that ignition happens. So for a combustion ignition engine like diesel engines, we do not need a carburetor. This carburetor is only needed for petrol engines. Again, there are few drawbacks of the carburetors for which it is now getting obsolete, and we are not using these carburetors for now. So let us go to understand the carburetor before understanding the advanced systems which are being developed right now. And before that, let me just check if there are any questions. Okay, no questions. I will go forward. So let us start by carburation. So carburation is the process of preparing in the spark ignition engine a combustible fuel air mixture outside the engine cylinder. Okay, so the main process of preparing a combustible fuel air mixture is called the carburation. This is a very complicated process and achieved in induction system. So in induction system, the way of preparing or the way of preparing a combustible fuel air mixture is by having a carburetor. But again, carburetor is not always required, which we'll know a little bit late in the subsequent sessions. So there's fuel injectors present nowadays in the injection manifolds, and accordingly the carburation is being replaced, means the carburetors are replaced and are not used. But for now, what is the carburation? It is the process of preparing a combustible fuel air mixture outside the engine cylinder. Then a carburetor is a device which atomizes the fuel and mixes it with the air, right? So at different conditions like very high, okay, let us we will talk about that in the subsequent slides. But for now, it's a device which atomizes the fuel. And what do you mean by atomizes the fuel? So it's which are having very very small diameters, and from that when the fuel comes out, it is very small droplets, almost like the atoms of the droplets. But that is not the case. Since graphically it is more like an atom, so it is atomizing the fuel. And when we atomize the fuel, the surface area to volume ratio is quite high. The surface area is very high, and that actually helps to vaporize the fuel automatically with the air. So that's the case of a carburetor, and it is the most important system of the induction, uh, important part of the induction system. So the parts of a simple carburetor includes the float chamber. So this is the float chamber wherein the fuel from the fuel pump, so in a car, in a bike, so the fuel will get first stored here before it is completely injected out into the carburetor. So the chamber which stores the fuel before injecting is called the float chamber. And why float chamber? Because it has a float. So you must have known by now what is a float, right? Because in the English uh, toilet systems, so while flushing, the container which contains the water, it has a float. So it is connected to a tap, and very similar to this, what happens is that when the water level decreases again, the tap gets open and the water flows inside the system, right, inside the container. Similarly, very similar to that, here we have a flow. When the oil level it decreases as the oil is being injected inside the system, so the oil level decreases. When the oil level decreases, the fuel from the pump is again enters, because the needle valve it now opens up. That is why the float is present, and this is a float chamber. Then we have the nozzle in metering orifice. So this is the nozzle having the discharge jet. So from the nozzle, the this oil is being sent into this whole carburetor arrangement, and we have a venturi. So this is a venturi out here. So venturi means a region of very small area or a area difference. So you will have this area is quite less, whereas this area is quite high. And now you will know why this kind of arrangement is preferred. So this is a venturi or the throat. Then this nozzle is placed at the center of the venturi. Why? We will know a little bit later. Then we have a throttle valve out here. So throttle valve is the valve when you are actually accelerating, or when you are putting your hands and putting your feet into the accelerator pedal, or the handle of your bikes, accelerator pedals in the cars, handles of the bike, you're basically rotating the throttle valve. And when you're accelerating it, when you want to accelerate it, then when you press it hard, what happens is the throttle valve it opens up, and more it opens, more the mass flow rate it allows to flow into the engine cylinder. And from here it is the choke valve, and from choke valve you have the air inlet. So sometimes you must have seen that when in this time of starting at the time of starting, sometimes the bike is not starting, or the scooty is not starting. When such kind of things happen, you actually adjust the choke. You just pull the choke so that very less amount of air now enters, and it is more rich in fuel. And when that happens, what happens is that the fuel it enters in a higher quantity, higher fuel air ratio, right, into the cylinder, and then the ignition happens. As the ignition happens and it sustains, you will find that the engine keeps on running, and when the engine keeps on running, it gets heated up, you again adjust the choke valve, or you open the choke valve now, then the air gets inside the carburetor. So that's the fact you must have all experienced in a real life. So this is the choke which you control from the pin that you have in the this bikes. Okay, and the pedal or the handle that you press is the you are controlling the throttle valve. So that's the thing from the practical experiences, and this is a part of a very simple carburetor system. So let us read some notes out here. The fuel level is slightly below the outlet of the jet when the carburetor is inoperative. Yes. So what happens is that the fuel out here, it gets discharged into this carburetor due to a pressure difference which is created due to the location of the venturi. And when the carburetor is inoperative, so you don't want the fuel to escape. In that, what happens is that this oil level, you see, this is in a very precise level, this oil level will be a little bit lower, and that way your this part will not exert a pressure in order to so the fuel will not escape out of this nozzle, because no pressure is being created. If the oil level would be a little bit higher, there will be a static head, a pressure head acting upon this nozzle, and that way the fuel will escape, right? So but if the oil level is lower, there no fuel will escape into the venturi. So that's how uh, it is designed, such that the fuel level is slightly below the outlet of the jet when the carburetor is inoperative. And also there is another pressure difference. Not only the static head of this oil level is driving this. No, there is an this pressure difference caused by the air flowing inside as well, and we will get to learn more about it. So that also causes the fuel to discharge into the carburetor. Then the nozzle has very fine bore. Yes, it must have. In if it has very fine bore, only then it can atomize the droplets. The very small droplets will come out from here. That is basically spray or discharge jet. And when such very small droplets come out, it easily get vaporized. Then the oil issuing from the jet is form of a fine spray. That is okay. It vaporizes quickly and mixes with the air. Okay. The airfoil mixture enters the engine cylinder and is controlled by the position of the throttle valve. Yes. So the airfoil mixture. So at the downstream of this nozzle. So by downstream you mean in the direction of the flow. So at the downstream, you will find that this area will have the mixture of air as well as fuel, and this air fuel mixture will now pass through this throttle valve. As the throttle valve is opened, so depending upon the amount of area it is exposing, you will find higher mass flow rates of the fuel air mixture into the engine cylinder. So that's how we are controlling the throttle valve. If we need more power, suppose, so we need more air fuel mixture to enter into the cylinder, more amount of heat addition, right? And more the forces it will be acting upon the piston. So we will open the throttle valve a little bit more, so that more mass flow rate is means enabled, and the more mass flow rate of fuel air mixture enters into the engine cylinder. So that is the introduction of a carburetor out here, and different parts of the carburetor. Very simple carburetor out here. So next we talk about the carburetor design. So carburetor design is basically there are various factors which influence the process of carburetors, which are as follows. So we talk about the engine speed, so the time available for preparation of the mixture, then the vaporization characteristics of fuel, temperature of the incoming air, and design of the carburetor. So let me first check if there are any questions. So far no questions. Okay, thank you. So huh now, various factors which influence the process of carburation are as follows. So first one is the engine speed, the time available for preparation of the mixture. So let us talk a little bit more on that. So these are the four factors on which the influence of the carburation are follows, so vaporation, then temperature, and the design of the carburetor. Now, I will actually give you an example. So, in case of modern high-speed engines, and for high-speed engines, let me remind you, which I have already talked about, and which I have talked about in my previous session. So, high-speed engines generally, instead of a four-stroke engine, uh, two-stroke engines are actually used. In two-stroke engine, one cycle is completed in one revolution of the crankshaft, and accordingly, heat addition is added in every cycles, every revolution. Accordingly, the very high speed can be obtained. So modern high-speed engines, the cycle is completed within one revolution of the shaft or two strokes, hence it's a two-stroke engine, and the time duration available for the formation of mixture is very small, because more the fast the it will revolve, more fast the whole stroke will complete, and accordingly, if the stroke is completed in very small time, so you will get more smaller time to vaporize the whole mixture, and then the mixture coming inside the cylinder, then again it is burning in the very next stroke. So you must be understanding the time duration of the formation of mixture is very small and limited. So to give you an example, the time duration of mixture formation in induction may be of order of 10 to 5 milliseconds, which I will show you in for in the process of an example. So let me show you that. So first, uh, in the mixture formation, there are few processes involved. That is atomization, mixing, and vaporization. The atomization means the very fine droplets coming out of the jet. It first has a very high surface to volume ratio. It first mixes with the air, and when it mixes with the air, due to the air present and the temperature of the air, it quickly vaporizes because the surface area is quite high in compared to the volume of the very small droplets of fuel, and it vaporizes. So these are the various steps which are required for homogeneous mixing, and it requires a finite time to occur, that we understand. So, for example, the time available for mixture formation is very small in high-speed engine. For example, in an engine running at 3000 rpm, the induction process lasts for less than 0.02 seconds. Are you understanding why 0.02 seconds? So I will tell you. For completion of this process in such small period, a very great ingenuity is required in designing the carburetor. That we understand. But why it is 0.02 seconds? So let me solve this problem for you. Like let me solve it in here. Ha. So we are given 3000 rpm, right? So 3000 are revolution per minute. So if we convert it revolution per second, so 3000 divided by 60, that is equal to 50 revolution per second, right? So 50 revolution per second. Now one revolution in 1 second, 50 revolution in 1 second. Now if we consider two-stroke engine, then we will have in one revolution, how many cycles will be covered? So this is revolution, one revolution, there will be one cycle if we are considering two stroke, right? Yeah, so one revolution is one cycle. If there is four stroke, then in two revolutions one cycle will be completed, but if it is two stroke, then one revolution is one cycle. Now if it is one cycle, that means it will have only one suction stroke. So one suction stroke per revolution, that you can understand. Why one suction stroke? So in the suction stroke only we need the air fuel mixture to enter into the cylinder, right? So in every revolution we need the air fuel mixture to enter into the cycle, and then we will have to see how much time it has for every revolution or every suction stroke. So we now have 50 rps. So 50 revolution in 1 second, right? Now, or 50 revolution means 50 cycles in 1 second. Then one revolution, which is again cycle, that is 1 by 50 seconds. And what is 1 by 50? 0.02 seconds. Now you must be understanding. So each revolution, in each revolution, each cycle completes within 0.02 seconds. And for each 0.02 seconds, we are having one suction stroke, and that is occupying lesser than lesser than 0.02 seconds, because for forming the vaporization, atomization, and mixing and everything, you will have to first form it very lesser than this 0.02 second, even in orders of 10. So actually, generally in the orders of 10 or 20. So divide by 0.02 divided by 10 or 20, suppose 20, that is around 0.001 second or 1 millisecond. So that's the case. So you see 10 to 5 milliseconds. So here I am showing you around 1 milliseconds. You will have to complete the whole vaporization and mixing process. And for that, that is a very, very small time, right? Now you understand why there's a very, very small time. So the whole point here is that since the time for induction is very less, the carburetor design should be such that it should be able to produce air fuel mixture and very homogeneous mixture of the air fuel at this very small time. So that is the whole point of this carburetor. And if we are able to design that, then we are successful in having a very efficient system. Next, in order to achieve high quality carburation within such short time, require good vaporization characteristics of the fuel, which are ensured by presence of high volatile hydrocarbons in fuel. Right. So more the volatility of the fuel, more easily it will vaporize and it will mix with the whole system, and that's what we want. So high volatile hydrocarbons are required, and that is actually rated with the number octane number, and which we will be studying in the subsequent sessions. Then inlet temperature also affects. So if the temperature of the inlet manifold is high, where the fuel droplets are released, then you must be you will feel that the if the temperature is high, it will have higher tendency of being vaporized easily, right? So that also affects the vaporization process. And at cold start, what happens is that in very cold countries, you will find the engine does not start very easily. Why? Because the temperature of the system is not that high in order to completely vaporize the fuel. The fuel is still in the liquid form, in the charge, which is passed onto the cylinder. And when the liquid form of the fuel is passed, it does not ignite. If it does not ignite, it will not it will not transfer the heat. Uh, it will not add the heat energy, and no work will be produced. So that way the engine does not start very quickly, and for that, for very cold conditions, there is a cold trap present, or very hot spots are present. These hot spots actually will work on the battery, and it will drive the power from the battery, and then it will warm up the engine. And after warming up the engine, when the charge is being produced, then the fuel, it vaporizes, and then the vapor actually nicely it mixes, it forms a homogeneous mixture, and that ignites in the cylinder. That's how it takes some time to start the engine at very cold countries. So for SI engine, the design of the carburation system is very complicated, owing to the fact that the air-fuel ratio required by it varies widely over its range of operation. particularly for an automotive engine. So for idling as well as for maximum power rich mixture is required. So we will now understand why for idling as well as for maximum power rich mixture is required. So uh, next okay. So before starting this, I think we should end in the carburetor design in this session. Um, we will take up what is the air fuel mixture that is required at different conditions, and what is means the appropriate air fuel mixture at idling, in cruising, and in power conditions. So again, I will also explain you the theory behind the carburetor design, how the mass flow rates of fuel and mass flow rates of air are calculated, and we will have the net mass flow rate, air fuel ratio. Then we will solve a few problems of the carburetors, and finally we will see how in modern systems, instead of carburetors, directly the petrol is being injected in the intake manifold, and how those systems are working. So that will actually complete our carburetors for now, and we will continue this in the next session. So I ready to take up any further questions if there are. I'll just see here. So is there any questions? So if there are no questions, then okay, then I think we can continue this in the next class. Thank you guys for attending this lecture, and I hope to see you next Saturday in in the next subsequent topics which we will be learning. Okay, then. Thank you so much. Yes, 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 obviously. Uh, this is a live session and it will be available in YouTube. So by tonight itself, I will be uploading this in YouTube, and you can go back and you can as much time as you want, you can see this video. And in the NPTEL lecture, in the announcement, there is one column where the spreadsheets of all the lectures are given. So in that you can directly click on the link of the YouTube link. You can see the videos in there, and not only this video, also the previous videos and of all. Okay, then. Thank you so much for attending. Bye bye. Have a nice day ahead.